respective team, like we use for some optimization purpose. Agree. Now, tell me, how do you choose this 5 minute? I mean, when do you choose this particular machine learning tool? When do you choose some deep learning models? When do you choose some genetic algorithms? When do you use some rough sets or information sets or fuzzy logic type approaches? How to identify? How to identify that in this scenario, I need such a machine learning model. We cannot use machine learning insistingly or forcibly because I have to use my machine learning model because I have to publish some papers. But in machine learning model, because here machine learning was not there in the beginning, now it is there. Still, there is previously also a lot of solutions were proposed. What was the use of artificial intelligence or machine learning model? They make it, I mean, even more effective. The performance of any particular solution is better than existing performance, obviously. So whenever you use some machine learning model, obviously we have to see for what scenario, for which type of machine learning model we really need to adopt. Therefore, you just tell me now how to select, because I'm sure many of you are doing some research in machine learning or related aspects, obviously. So you must have thought like, see, I'm sure somewhere you have used neural networks, somewhere you have used genetic algorithm type approaches and all. Can somebody tell me how to choose them? Just like that, I have some classification problem, I'm going to use some decision trees or neural networks. No, you have to see, right, under which scenario, which machine learning model. That is very important. Can somebody tell me? Am I audible? Please confirm.
Yes, sir, you are audible.
Yes. Please be
Sir,
interactive.
sir, I guess when you have a network topology which is too much dynamic,
Hmm.
so at that moment of time, might be this bioinspired technique might help at that time. Exploration and exploitation must be high.
Okay, so when more dynamic type nature of the problem exists in your domain, then you need some spam method. That you want to say, right?
Yes, yes, sir. Yes.
Okay. Obviously, you perform some optimization wherever you require some optimization required, that you use. Agree. But the exact scenario, okay, where do we use neural networks then? Why I'm discussing TDCs, there's no point in just learning what is spam intelligence. You should understand which scenario this is more adaptable. Then let me spend some 5 minutes time. Then we'll directly jump into spam intelligence.
When there is no chance for uh, more, as I said, more exploitation or more exploration in the normal machine learning type of algorithm,
Hmm.
I guess we try to go for such swarm intelligence type, wherein you
Okay.
can
Okay. I'll ask
dig
you a
even
same.
more.
Where do we use neural networks? You tell me.
Neural network, maybe a model-based type of model-based type of.
Even genetic algorithms also, fuzzy logic also, it's everything same list, right?
Correct.
Any other? Where do we really need neural networks? Don't confuse why we are talking about neural networks now. I will not go deep into neural network. Just I want to see where we use neural networks, where we use these bioinspired algorithms or spam
Sir,
intelligence.
When you want to
sir,
improve the results by you might have got some target output already. You have a target already that this
Hmm.
should be the output, and if you are not getting that, then you try to perform some back propagation and all, and
What
try to
about
reach that picture.
what about training? Training?
Yes, sir. Training. Yeah, that's
Okay.
what. Hidden layers will be. You increase the hidden layers. You try to improve the weights
Okay.
over
I'll ask
there.
the same question in a different way. Now there is no much training is given to us. Okay. Can we use neural networks?
No, sir. Yeah, now I got it. Maybe swarm intelligence will help in that way.
Right? Yes.
Yes.
So normally what we do, so now let me give a summary of this. See, there is a research problem where we have plenty of data, some labeled data. Labeled data is some supervised data. Why, what I mean by labeling that, you take some diabetic patient data. Patient one, see his name, some age, hereditary information, some smoking habit, drinking habit, so on. So then last column, what? Which class, whether he is diabetic, non-diabetic. Second row, second patient data. So and so parameter dimension 1, 2, 3, and so on. Then he belongs to non-diabetic. Patient 3, his age is something, his so and so something, his smoking habit, drinking habit, yes, no, smoking habit, yes, no. Finally, he is non-diabetic or diabetic, like that. This is label data. So you have large amount of label data. Okay, means what? You're already trained. You're already trained. Which means what? If this happens, patient is diabetic. If this happens, patient is non-diabetic. You're already trained. Therefore, what happens? By means of training, we get what? Learning. Do you agree? When we get training, we get learning. Do you agree? Hello?
Yes, sir. Yes, sir.
So, wherever training is given or possible in supervised problems, obviously learning is possible. Learning is obviously the result when training is taken. So these type of problems, supervised problem, where you are given with some training and you are learning, for such type of problems, your neural networks could be adoptable. Neural networks are the better solution. Why? Because you know how the central nervous system works, how the neurons communicate, and then on. So accordingly, we are going to use the neural networks. Assume that you are going to your office every day. So you already know the directions where to take left turn, where to take right turn. So you are already trained your neurons. Therefore, what happens? It is easy for you every day to go to your office in the same way. Somewhere you take left turn, somewhere you take right. So which means you are training your neurons. The main responsibility of neurons is what? Learning. When you train the neurons, they learn. Therefore, we solve the problem of reaching a particular location. So this type of training and learning problems, I'm going to use neural networks. Now, assume that there is no much training is given. There is no training at all. Then what will happen? You tell me. What is the consequence when there is no training? Somebody tell me. When there is no training. Simple, same example you take. You are going to office here every day. You are already trained. You know where to take left, where to take right turn. But if you are going to some unknown places, you have to reach somewhere, but you don't know the address, which means you are not trained. So where there is no training, tell me what is the consequence? Somebody tell me.
Will not the node will not learn. That is one thing. Or you can use something like a penalty and reward method.
Using we can use. What I'm saying is, now if training is not given, what is the consequence? Search space is high. Do you agree? Searching is high.
Yes, sir. It will take so much of time.
So much time, because see, same example, office every day you are going, you are trained your neurons, your brain remembers the location. So you are already trained. Because of training, learning happens. They remember every time how to go to office. When you're going to some new place, what will happen? You're not trained. Therefore, you have to search a lot. You don't know, you have to ask somebody how to reach the location. Searching is more. So whenever there is no training is not given, neural networks are not useful solution. Therefore, a lot of searching happens. Now, when searching is high, in such problem, we have to optimize. Are you following me? When searching is high, because no training is given, what we have to do? We have to optimize the distance, or we have to optimize the location where we are searching. We have to minimize the search space, right? There we call as optimization. That can be achieved by these bioinspired algorithms, SWAM intelligence, evolutionary computation, genetic algorithm models, etc., etc. Okay. So they are typically come under evolutionary computation model, genetic algorithms, SWAM intelligence, bioinspired. Mostly they belong to the nature computing models, nature computing. Okay. Nature inspired models, nature computing model. They all belongs to. Okay. So wherever we have training given, we go with some neural network type applications, because learning happens and I can see the weight optimization, some aggregation activity, all those things that we can. Anyhow, that is not our topic of interest today, neural networks. Now coming to SWAM intelligence, wherever there is no training is given properly, say since spaces, I have to optimize. For such problems of optimization, I'm going to use SWAM intelligence. Okay. Or genetic algorithm type application, some selection crossover, mutation type operation we perform. But today we are not discussing genetic algorithm, we are discussing SWAM intelligence. Similarly, genetic algorithm also you can use for search space. There is
मला सकाळी वाटलं असं.
Please all microphone unless you want to speak. So third is what? Linguistic type. Linguistic type, like fuzzy. Now the problem is not whether training is given or not, whether that is not the question. The linguistic type information, like I want to measure how good a person is. I simply can't say how good. I mean, he's good some 10% and bad some 90%. I can't say like that. So this type of linguistic analytical processing models, problems, where I'm going to use what? Tell me what I use here. Somebody guess? Fuzzy logic. Okay, fuzzy logic. So how we are going to use these neural networks or swarm intelligence or bioinspired algorithms, whatever it is, then deep learning, this fuzzy logic, rule-based mining, whatever it is. Okay, some fuzzy rule-based mining or whatever it is. So this is how we are going to talk about this selection of some machine learning model for the identified problem. Are we clear so far? Any doubts? Any doubts so far?
No, sir.
Yes. So now let us see. Now we have come. Now we are coming to swarm intelligence means what? There is no much supervised data provided to us. We are not got any much idea about the problem space because I have not given training. Therefore, I am going for optimization purpose using swarm intelligence. Okay. Are we clear? Why are we going for swarm intelligence now? Because there is some optimization need. Because there is no training is given. I have to go for some nature inspired model like swarm intelligence, bioinspired optimization computing model, etc. etc. Okay, so there are plenty of nature inspired models exist, like some swarm intelligence, other meta heuristic model, particle swarm optimization, ant colony optimization, dolphin swarm optimization, honeybee, firefly, gray vole, spider monkey, dolphin swarm. Plenty of optimization algorithms exist. First, let me define what is swarm intelligence. Can you see the slide for swarm intelligence? Confirm, please. The definition.
Yes, sir.
Yes. Now, by name itself, when we talk about swarm intelligence, because now we are into bio-inspired computing models. Okay. Now, tell me, why do we need to learn? I mean, some bio-inspired computing model. What do you mean by bio-inspired computing model? We are going to emerge some behavior, some intelligent smartness behavior, smart behavior. Okay. By observing certain things in the nature. Okay, some biological things. First, we talk about. So fog computing, cloud computing, also kind of nature-inspired model. They are evolved from the cloud, I mean clouds and fog related, but this is slightly different. Bio-inspired. They are maybe non-bio-inspired, but this is bio-inspired. So I'm going to observe a typical nature of a group of entities or agents and observe their intelligence, learn their intelligence, use it for some real-time optimization problem. So here swarm intelligence. Swarm means a group of particles, a group of objects. Okay, we call them as agents, particles, objects, whatever it is. Okay, their intelligence behavior I'm going to borrow, I'm going to observe, I'm going to learn and use it for some optimization. That is known as swarm intelligence. Intelligence inherited from a group of simple agents or particles or objects, whatever it is, called a swarm. Okay, so it is a group intelligence. Swarm nothing but a group. Okay, so intelligence taken from a group of objects called swarm. So swarm intelligence for some optimization purpose. Have you understood the definition of swarm intelligence? All of you? Tell me. Anybody? Any doubts?
Yes, sir. No, sir.
Now, swarm intelligence I'm talking. First of all, I'll ask a simple question. Why do we really need to learn some optimization models or some bio-inspired models? Why not humans can develop themselves? Why I'm asking is why we need to learn some ant colony optimization algorithm? Why do we need to learn from ants? Why we say ants are very small? Why to learn some optimization behavior from ants? Why to learn some behavior from spider, and then dolphins, and then many others? What is the main reason for that? Tell me. They are intelligent than us, is it? Obviously, they are intelligent, but why not humans who are ruling the entire world? Why not they can develop such models, and why they are understanding from others are non-humans? Tell me. Because we have seen the structure of this bioinspired models is I'm going to understand some behavior of some group of ants, group of birds, group of fishes, group of so and so. Then use their behavior. But here, do we really need to? I mean, why do we really need to understand such a behavior from group of agents like some ants, birds, or fishes, whatever it is? Because normally speaking, generally I'm talking about in humans, knowledge sharing is very limited. I don't say nonsense sharing is very high, but I mean to say knowledge sharing is very limited. Where in case of non-humans, knowledge sharing is very high. What do you mean knowledge sharing like training? Well, I already talked about training means learning will happen. Where in case of humans, knowledge sharing is very limited. If you speak for 1 hour, most of the time, I mean, the learning is very limited. Now, I'll give a simple example. Why we are learning still from non-humans still. If you see, there is a class of students, and normally if you see, sometimes there are some teachers, they give some questions in the examination from some secret source so that students can, I mean, students cannot copy from there, whatever it is. Now, if there is one student who cleverly identifies where the faculty or the teacher is taking the questions from in the examination, and if he prepares from there, and he will get the top marks in the examination. If he crack the source of information where the faculty is taking from while preparing the question paper. Now, if the same thing happens, when the student knows the source of information, he will be the topper. What will happen if the information is shared with every student? First of all, do you expect the student to share the information with every other student? Tell me somebody. You got the point. If there's one student who can cleverly knows where the student faculty is taking the questions in the examination from, then he can simply practice from that source and he can be in the top in the examination. But do you expect the student to share with every other student of his class? Say yes or no?
No, sir.
Mostly no, right? Mostly no.
Yes, yes, sir.
Now, what will happen if you share with everybody?
Everyone gets fun. So out of all.
So they will also score top marks. But whether this student will lose the top marks, no, right? He will not lose the top mark, but he will be on the top along with others, right? So this type of limited knowledge sharing is still there in the humans. Because of such reason, we are still learning from non-humans like a group of ants, group of birds, group of fishes, dolphins, octopus, spider, etc., etc. Okay, so our job is to understand such a knowledge discovery, such a knowledge sharing, how they are sharing the knowledge, what protocol they are following, and all. So for that, we need to understand certain characteristics of any SWAM network. Okay. So first and foremost, the characteristic is this is composed of many individuals. Are you following me? This particular what you call SWAM network, whatever we are constructing. First of all, I mean, whatever we are following or inheriting, it should have many individuals. Okay? The network should be composed of many individuals. What does this mean? This means there is more than one, like a group of ants, a group, more than one individual. Like, okay, there are many individuals, and all are homogeneous. Are you following me? All are homogeneous, and then they communicate based on some simple rules. Local interaction. Okay, only local interaction. Means what do you mean local interaction? They cannot speak globally. Means are the entire group. If there is a group of birds, every bird cannot communicate to every other bird. They can only speak locally. They can communicate or interact with the local birds just within its neighborhood or vicinity. Okay. Fourth is there is no centralized control. It is self-organized group or network. Self-organized network. There is no centralized control. Means what? There's no broadcasting like one say I will fly in this direction, all the other birds will fly in the same direction, something like that. There is no such criteria. Only they communicate locally and they have some agreement, and finally they will change the search direction with the velocity. Okay. So these are 4 characteristics of swarm network. First of all, there are many individuals. All are homogeneous. Means what? What do you mean by all are homogeneous? All are same. If there is one bird and other bird, they're same capacity, something like that. There is no one dominating a particle that will divert the entire group. No such like. Okay. Then third is, like I mentioned, they communicate locally. They cannot make a broadcasting communication or control over the entire group or swarm. Okay. The next is self-organization. There is no centralized control over the entire group. Okay. These 4 are the basic characteristics or criteria of any swarm intelligence network which you are following for your optimization problem. Are you clear with these 4 criteria?
Yes, sir.
Yes, sir.
Yes. Now let us see some swarm intelligence algorithms. Like we are going to see some particle swarm optimization and ant colony optimization. These 2 we'll see. And if time permits, we see the other. I'm sure many of you already studied basic algorithm, but just for the beginners, we'll talk about. Now, I've already talked about, because there is no training given, I'm going for this type of search techniques. Because there is no training, searching is high. That's why we call this as a random search technique. Okay. What about deterministic search technique? There are plenty. You must have studied a lot of numerical methods and other algorithmic cascades. There are many deterministic search techniques like branch and bound, steepest descent, Newton-Raphson, simplex-based technique, many, etc. But since there is no much training is given, and these deterministic search procedures are expensive because there is a large search space. Are you following me? Because there is large amount of search space, large volume space. Deterministic search techniques may work, but they're computationally, not efficient at all. Therefore, we are going with the stochastic or randomized search techniques like swarm intelligence, genetic algorithm, differential evolution methods, and stimulated annealing methods, etc., etc. Okay. Now, tell me, this swarm intelligence is what? Deterministic type? No, it is stochastic or random type search techniques. Okay. Now, I'm going to search in some direction. Like now, what do you mean by that? See, I'm going to when I'm going to working on my optimization problem, because there is no training, because search space is high, I'm going to start my search space. So what will happen initially? Where you are initially, where you are searching, what is the initial solution? That is called as initial solution. Okay. For example, a group of ants starting from the ant colony and going to search for the food. So initially they are where and which direction they are searching. So second criteria is search direction. Are you following me? Second criteria is search direction. Third is search direction is what? Initially I started at one location. I'm going to search in some direction. Next I'll change my direction, how. So search direction is very important. Where you are starting and which direction you are searching. Then third is how you are updating the criteria so that you can search in different direction. So where you are starting initially, which direction you are searching, and how do you change the direction, update criteria. Then finally, once you end up the optimal solution, how do you stop it? That's the stopping criteria. So initial solution, search direction, update criteria, and stopping criteria. Are you following me? So these 4 are the very important components of any search technique. Okay. Any doubts so far?
No, sir.
So for every swarm intelligence problem you are investigating or adopting, you have to see first what is the initial solution, what is the search direction, and how to update that. Search direction. Finally, how to, because once you come to optimal position, if you identify the shortest path or whatever it is, then we have to see where to stop. This is my stopping criteria. There is no better solution further. Unless we identify the stopping criteria, even though you get optimal solution, you will not identify that it is optimal, and you will go to some other non-optimal solution. Therefore, it is very important to see what is the stopping criteria. Okay. If you go with a better initial solution, what will happen? You will converge your optimal solution early as possible. Okay. And if you identify the better search direction, You can reduce this computational efficiency and computational complexity. Update criteria. How to update? How to reach? Iteratively towards optimal solution. Stopping criteria. Where to stop when the optimal solution is achieved. If this is not properly defined, you may end up with a non-optimal solution. Okay. So we are going to see how it works now. A group of birds or group of ants, how do they communicate each other, and then. So we already highlighted, it's a stochastic optimization type technique where we are going to, it's proposed in 1995, long back, PSO. Still, it is playing because of its robust efficiency. It is still playing crucial role in optimization related problems, computational efficiency, in large space problem. Now, this is a population based search method. What does this mean? Somebody guess? Somebody guess? See, when we say it's a population-based search method, it's a group of entities, a group of objects, a population. This is called as a population.
బ్యానర్ చేయించాం సార్ అక్కడ అదే ఒక ఫోటో తీసుకుంటే
Madam, anything required?
No, sir. No, sir. Sorry. Sir, please continue, sir.
Hello, sir.
Hello?
Sir.
Hello?
Hello, sir.
Madam, can you hear me?
Sir, we can hear you, sir. 1 second, sir.
Somebody muted me. Maybe I think when you are muting all, I think mine also getting.
Might be, sir.
Please cross check. When you are muting, don't mute me. Okay.
Okay, sir. Okay.
Can I continue now?
Okay, sir. Continue, sir.
Okay. So you can see the slides, right? Hello.
Yes, sir.
Yes. So we call as PSO as a population-based method where position of the particle is representing the solution. What does this mean? When you're talking about particle position is the solution, you should understand that, like, see, a group of ants are going from ant colony and searching for the food. They collect the food and come back. So when they're reaching the food, see, every position, like initially they're at ant colony going traveling some time, then finally reaching the food. So every location is a solution. Finally, optimal solution is what? When they are going get the food, collecting the food and coming back. So that is the optimal solution. So your position of the particle is nothing but a solution. And the searching agent is not one particle. The entire group is a searching agent. It's not one particle is going. Any doubts? So here, this PSO is a robust, we call it the evolution optimization technique because we are understanding their such a foraging behavior, and then based on the movement and their intelligence of their particles, we are going to make the optimization from here. So our job is to find the minimum value for the function, the optimum value. So if it is a bird swarm optimization, tell me what is a particle if it is a bird swarm optimization? What is a particle here?
Bird.
So bird is a particle. What is the solution? Food is a solution. So birds, here swarm is what? A group of birds, group of particles. So a group of birds, a swarm working for a solution, that is landing on the food. So a group of birds searching for the food in the sky. I mean, they're flying in the sky and searching for the food on the land. Then once they see the nearest food, they will land. The entire group lands on the food. It's not like one bird will go to one food, other bird will go to other food. No. Global optimum we are looking for. G-best. Global best solution. Okay. So, but see, like I mentioned, every particle in the beginning we have talked about, like they can communicate locally only. So here the best solution, P-best, what is achieved by a particle, that we call as a P-best. Whereas a global best solution for all the particles within the swarm is called as G-best. Our job is considering the P-best of every particle. I am going to talk about the global best. So it's very important to understand what is P-best and what is G-best within the particle domain. So while searching, we have to understand what is the best solution achieved by a particle and what is a global best solution, or you can say the entire swarm best solution, like the best value obtained by any particle in the neighborhood of the particle. Okay. So here the basic concept of PSO, when we talk about, it is actually nothing but how do we accelerate the particle position such that its P-best and G-best location can be identified, and finally how to find the best optimals, or you can say the optimal solution. Why we're saying acceleration is, now initially some group of ants are going for the food and in one direction they are going, and after some time what happens, we are going to accelerate some direction with the velocity of a particle, maybe an ant. So you are accelerating. According to what, you are going to find a better solution in different direction maybe. So our job is, like when we talk about PSO, if it's a bird swarm optimization, like how a swarm can, I mean, swarming is a group of particles or birds, how they share the flying experience and looking for the best solution in the search space. Here each particle, assume that if we want a common, I mean, general solution in a geometrical way, here each point is representing as a point. I mean, each particle, if you consider them as one point in open space, some n-dimensional space, where they adjust the flying experience. Flying in the sense, like if you take a group of birds, assume that they are imagining as one point in a space. Some 100 birds are flying in open space. So your job is what? Adjusting the flying. I mean the location, which direction I have to fly with what velocity and so on. So then according to what you can say, my own flying experience, I will see in which direction I am flying and how other birds are flying. Accordingly, I will try to change my direction and velocity. Finally, how I'm going to land on the food. So this is nothing but your entire swarm intelligence modeling. How do they work? Maybe for a bird swarm optimization. So if you see this example, okay, there is a particle X. Position is this particular direction initially. Now after some time it is really, this is my personal best. Now at this point of time, see, that is a point, is the location where I'm going to in this direction. This is my personal best, and finally I said this is my global best. Are you following me? So this direction I am flying, but this appear to be my personal best currently, wherein this is my global best. Therefore, I'm going to fly in the global best direction with a new velocity. Are you following me? This direction I'm flying, this is my personal best identified, because all of a sudden I have seen some new solution. It is closest to me, but what about the entire group? Whether it is optimal solution for the entire group, we don't know. You know, based on the flying experience from other birds or the other particle, I'm going to say this is a global best solution for every particle. Okay. Finally, I can change my direction with the velocity. Can you see the function for the this PSO x of t plus 1? Can you see the function? Please confirm. This
Yes,
is very
sir.
important slide.
Yes, sir.
Yes. See, all of you listen very carefully. Now, normally any particles from optimization binary square algorithms, most of the people what they do, Now you are working for some cloud computing problem, for some security problem, for some other network problem, whatever it is. Normal what happened, they'll propose, see, you can adopt some existing optimization algorithm and the fitness function like this, or you can propose a new fitness function. This objective function will define you how the velocities and directions are updated and how it is converging towards the optimal solution. So here x of t plus 1 equal to x of t plus v of t plus 1 means what? X of t is considered as a particle position. T is the time. So if I know the particle position at time t, x of t, if I know, I have to find x of t plus 1, that is t plus 1 where I will be, where I have to go. I means the particle, maybe a bird or a fish or whatever it is. So x of t plus 1 at time t plus 1, what is my position will be identified based on where you are at time t, plus what is the velocity at, possible velocity of time t plus 1, where you know v of t, the velocity of time t. Are you following me? I'm going to identify the particle position at time t plus 1. If I know the particle position at time t plus velocity of time t plus 1, where I know velocity of time t. So if I find velocity of time t plus 1, velocity at time t plus 1, where I know velocity of time t, that is v of t. So how v of t plus 1 is identified? Some weight, inertia weight. What is this inertia weight? Because when the particle observes some different solution, how do they change the s direction? There will be obviously some inertia is required. So some inertia weight multiplied by the velocity of time t plus some random constants c1 and c2 and learning factors are c1 and c2 are accelerating factors. Then some random numbers, what you can say 2, 2, 3, some two
First try.
because it's a randomized algorithm. Multiplied by p based and the g based related functions, or you can say the terms. Why? Because I have to consider what is my p based. I have to consider what is the g based for the entire star. And accordingly, I have to update some difference. I mean my velocity with a different direction. Okay. So this is very important. How the fitness of a particle can be identified, where velocity of a particular position, velocity of a particular time t is known, and t plus 1 I'm going to identify. So if v of t plus 1 is identified, everything is done. X of t plus 1 is a matter of just some addition. X of t plus v of t plus 1. Okay. So in most of the papers, what people are doing, either you can take the existing optimization algorithm and use it for same function, or you can take some optimization algorithm and improve the fitness function. Are you following me? Many of the people, maybe some PG level dissertations or whatever it is, some people what they're taking some existing optimization algorithm, simply adapting to their problem, optimization problem, modeling it. Then you see how much fitness value you will get it. Then accordingly you can accelerate the direction of the particle with the velocity. Where in case, if you want to make little innovation, you try to improve the function, or completely proposing new fitness function, how the velocities can be updated. This is how the particular simultaneous modeling can be used for your real-time optimization problem, maybe a network problem, maybe a security problem, or whatever it is. So this is the heart of this particle swarm optimization. This is very important. Either you can propose a new fitness function, or you can use the existing one, or you can improve the existing optimization. Existing objective function. Now, like I talked about, always global best. See, a group of birds are flying. Now, some assume 100 birds are flying. Now, some 10 birds will see nearest food is something. But for the entire 100 birds, that is not the nearest food. Then for some other 20 birds, some other nearest solution will be there. But that is not the nearest solution for the entire group. And similarly, there is one group of birds which you see that is the nearest solution for the entire group out of all the nearest solution. The solution is nothing but a food. Okay. So finally, we are going to achieve the global optimum like this. So if you talk about this in the view of bird swarm optimization, a group of birds are flying for the food. Tell me, how can I represent this alpha function? A group of birds are flying. How can I talk about this highest peak in the space? You tell me. It is a solution in which direction, when the entire group of birds are flying, the average distance a bird is flying is minimized. Do you agree with me? Assume that the group of birds are somewhere. If I say that this is the nearest solution for the entire group, where the average distance a bird is flying is minimized. Do you agree with me?
Yes, sir.
Because when we're talking about global optimum, see, assume that the group of birds are somewhere in the middle of the set space. This is the nearest possible solution, nearest better solution, where when all the group of birds are flying in this direction, what is the average distance a bird is flying is the least. If you go to other solution, every peak is a solution here. Highest peak is what? It is a solution in which direction when the entire group of birds are flying, the average distance is minimum. What is the average distance a bird is flying? Okay. But there will be some other solution which is very closest to the part compared to this highest peak. But that will not be the entire swarm solution. That's why we are going for highest peak, because it is very important to find this alpha function in any swarm intelligence modeling. Now, this is just a pseudocode for the particle swarm optimization, not algorithm. Initially, start with the each particle. How do we? So, while the termination condition we have, come to, for every particle, we are going to identify the fitness function. We already defined the previous function. Then we are going to update the personal best and the global best of each particle. Then what we are going to do? Update the velocity of the particle. See, initially we are finding P best and G best. Based on then I'm going to, because once I know what is my P best, once I know what is the best of each particle, then I'm going to update the velocity considering which is best, whether my personal best or global best, accordingly. Okay, using what? Equation 2. What is the equation 2? This equation. Okay. Finally, I'm updating the position of the particle using equation 1. Once you know the velocity of the particle using equation 2, then we considering which is global best, accordingly we can see the velocity, the position of the particle can be updated using equation 1, that is x of t plus 1. V of t plus 1 is the velocity, x of t plus 1 is the particle position, right? So now we talk about ant colony optimization, how ant colony optimization can be achieved here. Accordingly, we can understand the better. Can you see the slide for ant colony optimization?
Sir, slides are not visible, sir. Can you please share your screen once?
It is already said. Can't you see?
No, sir.
I think once I will. Can you see now?
Yes, sir. It is visible now.
For how long it is not visible? It was
just 1 minute back only, sir.
Oh,
Thank you, sir.
no issue. So now can you see the slide for ant colony optimization?
Yes, sir. Yes.
Yes. So now all of you listen carefully. You can understand. I know many of you studied already this basic optimization algorithm, but just for the beginners, let me recall it or highlight. Now this is another optimization modeling. Like we have seen PSO, ant colony, artificial bee colony, bird swarm optimization, dolphin swarm, firefly, honey bee, spider monkey, gray wolf, and octopus. Many are algorithm. Here, simple anti-colony optimization, which you can easily understand. Okay. So here what happens? A group of ants whose behavior we are observing. Okay. Now the behavior of real ant colony, which we are talking about here, which we used to solve some basic optimization, some discrete optimization problem. We are going to solve something like a shortest path problem. So how it happens? Let me explain. A group of birds are starting from ant colony and going to the food. Okay. N is the ant colony, assume that. Okay. N is the ant colony. F is the food. F is the food. So normally what happens? A group of ants start from ant colony and go for the food, collect the food and comes back. That is the major challenge in your problem. So the problem is, what if there is more than one path available to reach from ant colony to the food? From ant colony to reach the food, if there are more than one path exist, then tell me, what is our objective? From ant colony, if there is a group of ants, assume that some 100 ants are starting from ant colony, there are some k paths exist from ant colony, n to food f. Then tell me, what is the objective here?
Finding shortest path.
Yes, very good. Finding the shortest path. So a group of ants are starting at the ant colony, going randomly in different path, collecting the food and coming back. That is a normal solution. So here, what is the optimal solution? Ants should go in the shortest path. That's all. Now ants will identify, unlike humans. After certain time, ants will identify without any GPS device, without any IoT device, without any gadgets. They identify what is the shortest path. That is the beauty of this optimization modeling using bio-inspired computation. So let us see how it will work. So here what happens? A group of ants are starting from ant colony. Now there are k paths, assume that. Now in the figure, how many paths we have? Figure 1, N to F, how many paths we have? Tell me.
4.
It likes we have 2 paths, but actually
2
see,
paths.
when we take left, again we can take left and right. When we take right, again we can take left and right. I think there may be 4 paths, right?
Yes, sir. Yes, sir.
But
4
some
paths.
portion of the paths are overlapping, that is fine, but there are 4 paths. Okay, assume that there are some k paths exist. K paths from ant colony to the food. Initially, ant 1 will go to some path 1, ant 2 will go to some other path, ant 3 will go in some other path, and so on. So, assume that there are 100 paths, 100 ants, some k paths. Now, what is the probability that any random path is chosen by an ant? Tell me. If there are k paths. Tell me.
1 by k. Probability of selecting a path is 1 by k.
So there are k paths, it's 1 by k, right? Any path is being chosen equally. Why? Because all the paths are same at this point of time. Any path, any ant can choose any path, right?
Yes, sir. Yes, sir.
So now assume that ant 1 will go in some path, ant 2 will go in some path. Some 2, 3 ants may go in same path also, but randomly different ants are going in different path. Now finally, which ant comes at the food first?
Goes through shortest path.
So the ant that has chosen the shortest path will be the path which arrives first at the food, right? Right?
Yes, sir. Yes, sir.
Why? Why it is so? Why? Because if you observe, initially we have put a condition, all particles are homogeneous. All are same capacity. All are homogeneous. So when one ant is going in shortest path, one is going in longer path, since all are homogeneous, they will go with the same speed. So obviously what happens? The ant that has chosen the shortest path will come first at the food, right?
Yes, sir. Yes, sir.
Now it will come there at the food, collect the food and goes back, right?
Yes, sir. Yes, sir.
Now while going back, which path it will go back?
Again, the same path, sir. Same path that it has come from source to destination.
Now the question is, previously we said that every path has equal probability of being there. Now while going back, we want to send in the same path. Why? Because we know that it is the shortest path.
Yes, yes.
But
Yes.
how does the ant know it is the shortest path? Why? Because just because nobody is there, no other ant is there, that does not mean that it has chosen the shortest path. It may be confused that maybe some other ant has already come and collected the food and gone back.
Yes, 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 sir.
Do you agree with me, all of you?
Yes, sir.
Yes, sir.
Yes,
When the first ant comes at the food, collect the food, and while going back, we know that it is the one who is choosing the shortest path. But how does the ant know? Why? Because it may be confused and think that there may be some other ant has already come and collected the food and gone back. Maybe I am late. We can see that, right?
Yes, sir. Yes, sir.
So how to ensure that this is the shortest path? So here we use the intelligence of humans. So what we use, sorry, this ants, intelligence of ants. So normally any ant, whenever it travels in any direction, it will release something called pheromone. something called pheromone. Some maybe a gel or whatever it is. So whenever an ant passes in any direction, pass through, it will release something called pheromone. So whenever ant comes at the food and collects and gone back, and what will happen? So whenever it comes at the food and collected the food and gone back, I mean while going back, it will check which particular path has pheromone. Now tell me, out of all the paths, how many paths have pheromone?
Only one path.
Yes, only one path. Which path? Tell me.
The ants
Path is-
traversed.
Yes, the path in which the first ant had come to the food first, right?
Yes, sir. Yes, sir.
So, therefore, what will happen? Since there no other path has pheromone, this particular ant will conclude that no ant must have come so far because no other path has pheromone. The only path has pheromone is the path in which I have come. Therefore, I must have chosen the shortest path. Can it be guaranteed by this ant?
Yes, sir.
Yes, sir.
Why? Because you see, when the first ant comes at the food, and while after collecting the food, when it observes all the paths, it will see only one path in which I have come. That path has pheromone. No other path has pheromone. Means what? No other ant has come yet. Means what? I must have chosen the shortest path. So obviously, what will happen? This particular ant will conclude that it is the shortest path, and it will go back. Obviously, there is only one path as pheromone. It will go back in the same path because that is the shortest path, right? Any doubts so far?
No, sir.
No, sir.
Now, after some time, what happens? Second ant comes. What does this mean? Tell me. After some time, second ant comes. What does this mean? Tell me somebody.
That can observe the pheromone which is released by the previous ant.
No. What I'm asking is, you are right. But what I'm asking is, after some time, second ant has come means it must have come through second shortest path. Do you agree?
Yes, sir. Yes, sir.
Because we are starting with the assumption for now that all ants starts at the same time from ant colony. So obviously, when after some time the second ant comes, it must also be the second shortest path, the same order in which it has come, right? You agree?
Yes, sir.
Now, when the second ant comes and collect the food while going back, now again is it same like all paths have equal probability of being chosen? No. From while coming from ant colony, no path has pheromone, so everything is a beginner now. But after collecting the food while going back, it will see. Now tell me how many paths have pheromone?
So two paths.
Number of
Two paths, right? One path, that is the first ant chosen path, that is the shortest path, and the second shortest path in which the second ant has come. Do you agree?
But the concentration of second shortest path is more, sir, as compared to the first one because of time.
Can you
That's
repeat?
concentration of pheromone in the second shortest path is more as compared to the first one.
Now see, you're right, but when it comes to the, now I'm talking, okay, since you have started this, now tell me how now second ant will go back in which path? Obviously, see, there are two paths of pheromone. One is the first path that was chosen by the ant one, and the second path in which it has come. So there's no point in choosing other K-2 paths, right? Now, from these two paths, the competition we have, which path it will go back?
That only, sir. When in which path the pheromone concentration is more, it will select that one. Because
okay,
obviously,
according to you, just now the second ant has come, so it has more pheromone. So,
yeah.
It will go back in the second shortest path.
I mean so.
Yes, you are right, but that's why we are using the intelligent behavior of these ants. That's why we are still learning from ants. When the second ant comes here, it will see that while after collecting the food or before collecting whatever it is, it will see that by that time I have come already one path as pheromone. So here not the question of the concentration of the pheromone. Once it comes, collect the food, it will see by that time I have come already first path as pheromone means what? I must have not come in the second path. I must have come in the second or third shortest path. Therefore, it will go back in first path ant. I mean first ant path in which the the shortest path. Are you following me?
Agree, sir. But what is the role of pheromone then? Because pheromone evaporates. Therefore, obviously, the first
Pheromone
shortest. Yes, sir.
Sir. Pheromone is evaporated over time. I agree. Now, our objective is to find the optimization at the, earliest. Now, when the second ant comes here, now the competition between the first shortest path and the second shortest path. Now, see here, the question of getting the shortest path, whether at this point of time or after some time, again, we are going to choose the shortest path. Now, when the second ant comes here, by that time it has come already there is one ant is with the pheromone. So if you go with that logic, second ant will choose the shortest path of the first ant. Now, okay, now assume that after some time third ant comes. Now tell me how many paths of pheromone? Three paths of pheromone, right? After some time. Now you see how many rounds of pheromone we have. Shortest path 1. Hello.
Yes, sir. Yes, sir.
What I'm asking is same logic I will go. Pheromone is evaporated over time after, obviously. Now after some time third ant comes in third shortest path. Assume that. Now whenever it comes and collect the food, while going back, how many paths of pheromone now?
Three parts.
Three paths, right? Now first shortest path, the closest path. How many rounds of pheromone it has?
Participant, please mute yourself. There is some disturbance.
Simple logic. You see, now we are talking about, see, when the second ant comes, there is only, by the time it has come, there is only one path as pheromone. So there is no problem, because obviously it has come means it must have chosen the shortest path, the ant 1, it will go back in the shortest path. What about third ant? After some time, if the third ant comes, collect the food, while going back, you will say, by that time I have come already 2 paths of pheromone. Now you see, first path has how many rounds of pheromone here?
2.
2 rounds, right? One is by the first ant.
Yes.
Second is the reverse direction by the second ant.
Yes, sir.
Okay. Now, so it will go back in the first path direction.
Definitely.
Right, obviously. So now tell me, after this one, first path has how many rounds of pheromone?
3.
Second ant?
Second and third.
1.
Already first has gone. Second also follows the same path 2 times. And now third is going. So 3 times.
So if you see over the time, whatever it is, whether second ant will go back in the same path or go back in the first path direction, over the time what happens? Over the time, this one particular path is exclusively used.
Yes.
You all agree with me?
Yes, sir.
Of course, now the same logic may not work if you change the time scenario, like, because pheromone is not a permanent remark given by an ant. It is just a biological, the second ant comes after a certain amount of time, the pheromone may not be identified. It will assume in which it has come is the shortest path. The second ant path will remain as the shortest path.
Okay.
Therefore, pheromone is evaporated over time, but whether second ant will go back in the same path or the first ant path, over the time, this after some time, see here how fast we achieve the optimization, that matters. So now the logic I'm asking, when the second ant comes here, by that time already it is there, pheromone means it need not to see which particular pheromone has more amount or more concentrated. Because already by the time I have come, already some pheromone was there in the ant 1. So why second ant should compare its pheromone with other plant? That's my logic. So
Okay.
my job is to achieve, optimization at the earliest. Even second ant go back in the direction after some time, again over the time, the shortest path will be the closest, will be chosen by each and every ant.
Okay.
Okay. Now, so finally we have achieved the shortest path after certain trials or rounds of learning. Now this is all what I call as learning. Initially starting from any random path, arriving at the food, coming back, and then using pheromone to understand which is the shortest path. After some time, second ant comes and it will also learn something, then go back in the same direction. Then third ants over the time. Now see, if the same logic go over the time, even from ant colony to the food also, we need not take any random paths. Do you all agree? Why? Because initially no path was visited by any other ant. So while coming from ant colony to the food also, we are taking random. Now when some remarks are made from food to the ant colony already, so while going from ant colony to the food also, we can see the path in which more pheromone is there. So obviously what will happen? So from source to destination, destination to source, every time we use the shortest path. It is not only from food to the ant colony. Over the time, what happens from ant colony to the food also, we are going to use the shortest path. Do you all agree with me?
Yes, sir. Yes, sir.
Yes. So this is how a group of agents, simple agents like ants, they achieve the optimization by just observing their biological behavior, like pheromone or whatever. So tell me, where do we use these type of optimization problems? I mean, optimization algorithms. Which real-time problems? Somebody tell me. Because we have seen a lot of challenges. Now we should also see what are the applications, right? Tell me.
Repeat, sir.
Yes. Just 1 second. So can somebody tell me what type of applications we can use this type of optimization problem?
To track for in the tracking of thieves and all.
Pardon?
In the tracking of thieves, gangsters, and all after.
Okay. Any other?
Traffic, road traffic, sir, finding the shortest path.
Yes, GPS and maps related other type of problem we can use. Some, and then these cabs and Ola driver, Ola cab, Uber and all those things. The traffic management. Yes, you're right. And now see, normally if you see, there is a source, there is a destination, there is a vertex to vertex, there are several edges available, several paths available. So all these problems, where and all, you can use this Bellman-Ford and your shortest path, what is called your distress algorithms, Bellman-Ford network shortest problem, and network flow problems, shortest path problem, routing in sensor networks. Like we have source to destination, some gateway to base station or sensor nodes or mobile towers or whatever it is. So this type of network problem where routing is needed, this type of problem, set cover problem. Normally wait and all, it's simple logic. You have a vertex, in between a lot of edges we have. So how to find the optimization, shortest path for this type of problem, network management, traffic management, plenty of problems we have. All and all you can use. Okay. So the same thing, whatever I've explained, how the group of ants will go back. So how the shortest path we have identified initially, and how a group of ants will go back, and finally, how to go over the iteration, how the ants will go back in the same path, and how we are going to understand their behavior. And after some time, see, the shortest path is almost exclusively used by all the ants, from bird nest to, from the ant colony to the food. We call it nest or ant colony to the food. How we are going to use it. So different applications of PSO, how we talked about, like we have shortest paths and routing type problems, and assignment problems, and set problems, and plenty of even traffic problem, whatever and all we discussed. So similarly, we have genetic algorithm related, but here I will just ignore this. So now the fitness function, what we are talking about, like velocity of time t+1, how with the inertia, and then with the personal influence, with the social influence. If you see, it's very simple to understand this problem. How I'm going to identify the velocity of a particle at time t+1. Okay, where I know the position of the particle, I'm going to identify. So here, initial some inertia because I'm going to change this velocity and direction. And for each particle, I'm going to see what is my personal best. And finally, with the social influence, like, see, the personal best says what? This is your closest solution. Social influence that tells what? This is a global best. And you have to, you have to go with the global opinion. Therefore, after adding this particular term in the social influence, then with the personal influence and with the inertia because of the change in the velocity and direction. Finally, how I'm going to identify the particle position at time t+1, where I know the velocity of time t+1. So particle velocity, we are identifying like this. Here, the inertia normal is required. It used to make the particle, because we have to make the particle to move in the some direction with the same velocity, right? So obviously, we are going to make it with such an inertia. What about personal influence? Because we have to improve, like this is my personal best, and how I'm going to identify the global best with my personal best consideration is given to the entire group. Okay. So how can I go to the previous position, and how to identify the better position where I can reach the optimal solution. Then finally, how to reach the best particle position so that the entire swarm can reach the global solution. So these three are very important. First term is inertia, next is personal influence, third is the social influence. This we already discussed in the previous slides. So this is known as, first term is known as the diversification, and the second terms where the personal best and global best are integrated, and then accordingly the particle position can be redefined to achieve the global best solution is known as intensification. The PSO, how we are going to identify these two intensification, because we have to see the previous solution, how the best solution can be achieved, and where in case of I'm going to find the new solution and find what exactly the next possible solution can be identified. And similarly, birds from optimization, how we can achieve a group of birds are flying in different directions. Same logic, but I will not spend much time here. Like each particle here, each particle is a bird. Assume that they're flying with some different direction and velocity. Assume that arrow indicates the direction in which it is flying, and then each color object indicates a solution or a food. If you see there is a top right particle, there is a nearest solution adjacent to it. Still, it will not go in the direction. It will change its direction towards the bottom one. There is another one, and accordingly, it is going to understand the particle position better, and then it is going towards the best particle position. Finally, if you see, there are some 5 particles are close to one particular food or objective. Another 6 particles are close to different food and objective. So obviously, what happens? These 5 particles will have to go to those 6 particles, or those 6 particular birds will have to fly in the direction of the 5 particle. So tell me, which one is global optimum here when we talk about the particle position and the personal best? Tell me. Somebody tell me. So obviously, what happens? We are going for global best solution. These 5 particles will have to fly in the direction of 6, rather 6 coming down, because we have to minimize the average distance a bird is flying. Are you following me? You see this.
Yes, sir.
Finally, all the particles are landing on the food. So our job is global optimum. That's why we call it that Alpine function we have seen. Na? The global optimal solution, how we are going to achieve here. So the same logic, how we are going to find the solution with a better value here. So bird flocking algorithms, bird flocking model, how we are going to use similar objective. So in bird flocking model, normally we try to follow some 3 simple rules. We try to avoid collision with the neighboring birds. Normally, see when we are like if you see in the first slides, we discussed about having all the particles are same and homogeneous and they communicate locally. So when you have only local communication to talk about its personal best and the global best related factors, obviously when you have disagreement with the neighboring particles, neighboring birds, what will happen? You will definitely may not, work in the direction of optimization and the global best may not be possible at the end. So we should always avoid collision with the neighboring birds. If you say this is the personal best, if some 3 birds say that is the personal best or global best, then we should go accordingly in the direction of that. So we should avoid collision with the neighboring birds. That's how we'll try to make the solution here. Fine. Second is match the velocity of neighboring birds. How we are going to match the velocity? If you see a particular bird, we should not even not only this bird swarm optimization also, even ant colony optimization also. If all the particles are not homogeneous, because we have put a characteristic of any swarm network, all the particles are homogeneous. If here all the particles are not homogeneous, then if one particle is not matching the velocity of others, obviously what happens? Sometimes a non-optimal solution may become an optimal solution. You take ant colony optimization algorithm. First ant go in shortest path 1, second ant go in shortest path 2, the second shortest path. If the velocity of the second ant is high, more, then the speed, obviously what happens? Second ant will come first. Then over the time what happens? Second shortest path may be chosen as a shortest path. So this type of problems, inconsistencies may come in the solution domain. Therefore, the second rule is we should match the velocity of neighboring birds always. Of course, we have defined the characteristics of any swarm network, but of course, normally we should follow this type of velocity. So first is collision avoidance, second is velocity matching, right? The velocity matching, and third is the flock centering. You should always stay near neighboring birds, rather deviating from the group or swarm. If you say near neighboring birds, then it is easy to communicate. Local interaction is possible, and then accordingly we can decide in which direction we can fly for the better set space. We are going. So these simple rules we have to follow, and there is no centralized control for the entire group structure. Accordingly, we can perform. And so finally, the same definition we are going to use for optimization purpose, with the help of which we are going to do. So I think we are done. Any doubts? Let me know. We have some, I think, 5 minutes time. Am I audible?
Yes, sir.
Yes. If you have any doubts, let me know, please. We have some 5 minutes time. I will give this 5 minutes for question answers. No doubts? Participants can ask.
Thank you, sir. Thank you for your valuable speech and talk. Hello, sir.
Yes, madam, I can hear you. Participants, no more doubts? You ask any doubts, I can clarify. I think it appears they have no doubts. Any other queries? If not related to this topic, any other queries also you can ask.
Sir, may I ask a question?
Yes, please.
So many swarm optimization techniques are available. So how do we decide in what application should we apply which technique?
Yes, madam, that's a good question. Now, what happens? See, normally, you take this ant colony optimization algorithm. It is suitable to certain type of optimization problem like routing, set cover, or any network coverage type problem. So here, normally what happens? There are plenty of optimization algorithms exist. So we have to see first which type of algorithms are adaptable to our problem. See, if you choose one optimization algorithm works better, that does not mean that others, don't work. Our job is to identify which algorithm is more adaptable to these type of problems. Accordingly, we have to identify. So for that, maybe you have to do some kind of, literature review. That's all. See, if you take a routing type problem, ant colony optimization algorithm and gray wolf, spider monkey type algorithms may be adaptable. Similarly, normally what happens now? You have to understand this set space. What type of particles are there? See, a group of ants, the way they behave is different. A group of fishes, that is different. A group of birds, it is different. So, ant colony optimization algorithm, birds flocking algorithm, and other dolphin swarm optimization algorithm, everything has different characteristics. So, first you have to study the nature of optimization algorithm. What type of particles are there? What type of behavior they emit, and what type of optimization we can make over there. Then you come back to your problem domain. Then you see out of these optimization algorithms, which can be more suitable. Okay, and there is no one optimization algorithm that can be applicable to all, because obviously this is actually like custom. I don't say customized, but this is like application-oriented optimization algorithm. Like one routing related, some are suitable. Something load balancing, energy efficiency related, some other optimization algorithm. Localization related, some other optimization algorithm. So normally, if we talk about the sensor networks or any network problem, localization related, we talk about dolphin swarm optimization algorithm and other type of optimization algorithm. Load balancing related, gray wolf we can try, and then shuffle frog leaping, shuffle complex evolution optimization algorithm, and then spider monkey algorithm we can try. Routing type ant colony, and then I think few more algorithms are there. So it depends on the application type and the nature of the optimization algorithm. So both you have to refer first. Your problem domain you refer, what type of data you have, what type of nodes you have, what type of connection you have, similar behavior, which optimization algorithm you have, accordingly you can identify.
Okay, thank you, sir.
Yeah. Any other doubts?
Okay, sir. Thank you for enlightening us.
Yes, thank you, madam. Thank you. I think we have another session 11:45 maybe. So we can conclude here. Thank you very much.
Okay, sir. Thank you, sir.
Okay. So, Lani, madam, thank you. I'm leaving now.
Okay, sir. Thank you, sir.
Right.
All the participants, please take the break for 10 minutes, and we will join back again at 11:40. At 11:40, the session is on classification rule mining using bio-inspired algorithms. We will join back at 11:40. Thank you.
Priya ma'am, how do we have the attendance?
Ma'am, we'll place the link in the group, ma'am.
In the WhatsApp group.
Yes, ma'am.
Okay, thank you.
And for the next session, we have to join with the same link, right?
Yes, ma'am. Same link.